The very first known camera, that is not something film recorded, but camera, dates back to Aristotle. And here's an image, and it's called camera obscura, which is from Latin, means darkened room. So those of you who speak any Romance language, comma bed, camera from room, obscura, darkened room. By the way, there's a cool museum in Edinburgh called Camera Obscura, which is all about the history of cameras and photography. I highly recommend it, although I didn't go there because I was in the Scotch Museum. And here you see the idea of a room with also a small hole in it. Okay, that's the aperture, projecting on a white wall in the back. In fact, there was a nice quote from Da Vinci. I don't know how you get quotes from Da Vinci, but I guess he wrote them down. Or maybe it was on Memorex tape, I don't know. It says, when images of illuminated objects penetrate through a small hole in a very dark room, you see on the opposite wall, these objects in their proper form and color, reduced in size in a reversed position owing to the intersection of the rays. Okay, and that's what we were showing before. And by the way, those of you who think about lenses and focal length, the focal length of that system was the depth of the room. All right? So how does that aperture affect the image that we see? How does the size affect the image? Here's a demonstration taken from Paul Debevec's website of making pinhole cameras. And you can see on the left that he actually took a piece of foil and he's mounted it directly on an electronic imaging system. On the right is the picture that was produced using this camera, and presumably he had to worry about leaving the shutter open long enough to get the proper kind of exposure depending upon the sensitivity of the sensor, and we're not going to talk about imaging and sensitivity in this course. The first thing you might notice is, boy, that's an awfully blurry picture. And the question is, why so blurry? We just said that when we put a really small hole, it only lets a single ray of light in, and so it should be nice and crisp. Well, the problem, of course, is that there's small and then there's small. And so the question is, how big should the aperture be? So here is an actual rendering using a pinhole type camera, where they're showing you the different size of an aperture in terms of millimeters, and the ability to see a crisp image on the other side. And you notice when it starts out at 2 millimeters, you get a pretty blurry picture. And another way of saying that is 2 millimeters is large compared to the rays that you want to try to capture. And then it goes down to 1 and 0.6, and finally 0.35 millimeters gives us a pretty nice rendition. So the question you might ask is, well, why not make the aperture as small as possible? I mean, the smaller I make it, the smaller number of rays that get through and the crisper it will be. And the answer lies in, let's see, somewhere in physics. Maybe you played with water tanks where you cut little slits and you pushed waves through them and you caused ripples to change. And then you learned about something called diffraction, okay, and how waves interfere. And with light, what happens is if you make those holes too small, you start to get diffraction effects. So at 0.35 millimeters, we had a nice crisp picture, but then things start to go bad, and then when it gets even smaller, not only are we getting less light in, but we're starting to get things blurred out again. And that's because of diffraction effects. So you have to worry about those kind of things if you were making pinhole cameras.